Water rushing through a municipal treatment plant, assembly lines pressing tons of steel. We rarely think about the raw mechanical forces keeping modern cities alive. Decades ago, humans controlled these physical forces directly, pulling heavy analog levers and throwing physical switches on the factory floor. Today, those levers have been replaced by software, and software can be unpredictable. During a routine network assessment at one facility, an engineer initiated a simple ping sweep, a basic connectivity check. That digital ping accidentally woke up a controller, causing a 9-foot industrial robotic arm to suddenly swing 180 degrees across the room. This is the realm of operational technology, or OT. When IT systems fail, we lose data. When OT systems fail, motors overheat, valves burst, and people can get severely hurt. The physical safety of our world relies entirely on the digital interfaces controlling these machines, making them a prime target for attackers. To understand how a cyber attack translates into physical damage, we have to look at how a modern control center is built. At the very bottom of the industrial stack are programmable logic controllers, or PLCs, and remote terminal units. These are the physical computers wired directly into the machinery, speaking in raw binary code to open valves and spin motors. Humans don't speak binary, so sitting right above the PLCs is the Human-Machine Interface, or HMI. It acts as the translator, taking a tap on a screen and converting that human intent into the specific machine-readable code required for action. That translation works in reverse, too. The HMI pulls continuous data up from the physical floor, giving operators round-the-clock visibility into energy yields, tank temperatures, and critical system alarms. The HMI is the literal, essential bridge connecting digital intent to massive physical force. For years, these systems were air-gapped, physically isolated from the outside world. But the drive for operational efficiency pushed facilities to connect their OT networks to corporate IT systems, and eventually to the internet. That connectivity created an enormous blind spot. Today, highly sensitive HMIs are frequently left exposed directly on the public internet, easily indexed by specialized search engines like Shodan. Attackers don't even need sophisticated malware to breach these systems. They simply look up an exposed IP address and use a default vendor password or a legacy shared account to log in and shut down the infrastructure. Once inside, bad actors can execute a man-in-the-middle attack. They intercept the data stream, secretly altering physical set points on the PLCs to push machines past their safety limits, all while sending spoofed green everything is normal data back up to the operator's screen. In the rush for remote convenience, we inadvertently turned our most critical control bridge into a highly visible open door. We cannot revert back to analog levers. Instead, securing these environments requires a strategy called defense in depth. Defense in depth builds redundant walls around the HMI. If one layer breaches, another blocks them. The first step is microsegmentation. Strictly isolating the HMI and its controllers ensures a breached corporate email doesn't provide a direct path to the factory floor. From there, facilities implement protocol whitelisting. Firewalls are configured to deny all traffic by default, only permitting known, safe industrial commands, like Modbus, to pass from the HMI to the PLCs. Shrinking the network battlefield is the mandatory first step to locking down the physical plant. But securing the network isn't enough if the user accounts themselves are compromised. The legacy practice of using a single shared operator password must be replaced with individual authentication tied directly to enterprise identity providers. This enables role-based access control. Merely hiding a start motor button from a junior operator is useless if a hacker bypasses the visual interface. Real security happens at the back end. The API must explicitly verify digital clearance before passing commands to the PLC. Securing the human-machine interface is no longer an optional IT chore. It is the foundational requirement for public safety in the modern automated world.